Thank you. I'm delighted to be here, although this is a very broad speaker series, and I easily could have mispitched what I'm going to tell you, so we'll see what happens. So people do some very impressive things. The kinds of inferences they make from sparse perceptual input is astonishing. The way that they control their bodies and motor control is pretty impressive. Their social inferences are quite sophisticated, as are their linguistic inferences. And many of these fairly rich behaviors seem to be pretty well often captured by the notion that perhaps people are doing something like Bayesian inference, some kind of rational inference. On the other hand, though, they make some interesting mistakes, and those interesting mistakes have long been documented via a set of biases and heuristics. This is a slightly edited list of cognitive biases from Wikipedia. I eliminated a few things that looked like obvious redundancies, added a few things that were clearly missing. This is in the ballpark of 170 of them. So with this astonishing list of biases, it would seem that, well, one of several things must be happening. Either we've really figured out everything that's going on, or something is amiss. And it so happens that many of these biases don't yield too much predictive power in the real world. When people try to measure in field experiments and markets how much these biases play a role, it turns out very little. I mean, some of the reason this happens is that many of these biases have a role sort of at the margin of being very, very uncertain and maybe even indifferent. Things like framing effects. If I tell you that a given treatment will save 30% of people from hepatitis Z, or 70% of people will die during hepatitis Z. If I tell you that they will die, that's bad. If I tell you that 30% will live, that's good. However, if I were to tell you that the treatment was being administered for a common cold, wherein you have quite a bit more expectation about how likely the treatment is to work, you're going to not see this effect at all because you have zero, essentially, uncertainty about what's going on. The other reason that these don't seem to yield too much predictive power is that many of them are really perfectly contradictory with no way to adjudicate between them. For instance, there is an optimism bias and a pessimism bias. There is a better than average effect and a worse than average effect. The gambler's fallacy says that if you see a sequence of deviations from average, so if I'm flipping a 50-50 coin and you get 3 heads in a row, the gambler's fallacy predicts that you will now expect to see tails because you're more likely to have something that reverts you to the mean. The hot hand illusion, on the other hand, says that if you see some deviation from the average, like if I see somebody make more shots than I expect them to make, I will expect them to continue deviating from the average in the same direction. So that basically, if you have a deviation from the norm, the gambler's fallacy says you'll get some mean reversion, and the hot hand illusion says you will continue that deviation. Obsequiousness and reactance. Obsequiousness suggests that people will do what they think other people want them to do, or like the experimenter. Reactance says that when they think people expect something of them, they will do the opposite to assert their free will. Base rate neglect says that people largely focus on the specifics of a given situation or individual rather than the relevant base rates. Stereotyping biases suggest that people don't pay attention to the specifics and instead go with generalities about a group. In memory, bizarreness effects say that people will remember outliers that are weird compared to the set. Typicality effects say they will remember things that are common and normal for the set. The fundamental attribution error says that people tend to over-attribute human behavior to the disposition of the agent, whereas the extrinsic incentives bias suggests that they tend to impute hidden motivators outside of this person's agency. So many of these biases simply point in completely opposite directions. So what you get then is a lot of explanatory power, because if you have effects that can essentially explain either direction, either deviation from what will be optimal, they can certainly explain everything, but very little predictive power. And so what I'm going to tell you about is some work that I and others have been doing, trying to figure out if maybe some of these things can be explained not in terms of postulating a number of weird effects and biases, but in terms of some kind of generalized rules and principles about how people reason and what happens. We haven't gotten very much success. You can see many of these are still not filled in. But there's essentially two classes of strategies that I'm going to tell you about for explaining why perhaps some of these biases exist. One is that deviations from what you might people would have considered to be normative behavior arise largely because people are doing something more sophisticated than the people who were calculating the normative behavior were expecting. That people are doing something more richer and more probabilistic than people thought. And the other one is slightly more complicated, and it's that when people are doing this kind of rich probabilistic inference, they have to do so in light of their cognitive limitations, and so their inference process for doing probabilistic reasoning is constrained by resources, and therefore when they adopt resource-constrained inference algorithms, you get characteristic patterns of deviations from the optimal answer. So I'll dive in by telling you about these two things, which is the extrinsic incentives bias and the fundamental attribution error. And this is work done with my students Drew Walker and Kevin Smith. So the fundamental attribution error was first documented by Jones and Harris in 1967. What they did is they gave subjects essays that were ostensibly written by another person. These essays were either pro-Castro or anti-Castro. For a long time, this pro and anti-Castro was bizarre and irrelevant and nobody cared about it, but now we can talk about it again and everybody knows who Castro is again. This is delightful. So if you get an essay that's pro-Castro and I tell you that the person who wrote it had a choice about whether to write in support or against Castro, you are of course going to assume that the author is actually pro-Castro insofar as they wrote a pro-Castro essay, or against Castro if they wrote an anti-Castro essay. However, if you were told that the position of the essay was assigned to the author, you still believe that people who wrote an anti-Castro essay when they were told to write an anti-Castro essay, they themselves have some anti-Castro beliefs. And people who were told to write a pro-Castro essay still have some pro-Castro beliefs. Now, this clearly is an error, right? Because you have sort of two candidate causes. Either the instructions are the reason why people wrote this essay, or the person's actual attitudes are the reason why they wrote this essay. And if I tell you that they were given instructions to write an essay in support of one thing or another thing, that should explain away any reason that any attitude you might infer for this person. And so this fundamental attribution error that people over-attribute to disposition is essentially a staple of social psychology. It's in pretty much every textbook. It's in much of popular press. So people over-attribute to disposition. On the other hand, if I give you the same pro and anti-Castro essays, in this case they were pro and anti-marijuana legalization, a little bit later when people forgot who Castro was. And instead of asking you to infer the attitude of the author, I ask you how much pressure was put on the author to write an essay in favor of this position while I tell you what this author's attitude was. If I tell you that they had no opinion about the essay, about marijuana legalization, and they wrote a pro essay, then you infer that the instructions and the situation asked you to write a pro-marijuana essay, and if you read an anti-essay when the person ostensibly had no opinion, you infer that the situation encouraged them to write an anti-essay. However, even if they had an opinion, if I tell you they had a strong opinion when writing this essay, you still infer some situational pressure and in favor of the position of the essay. So it's exactly the same effect in exactly the same direction, but now you're inferring situation rather than disposition. And so if perhaps this were the thing that we found first, the fundamental attribution error would say that we are inclined to over-attribute to situations. So the logic of why this is an error makes perfect sense if we think about deterministic systems. So if I tell you that a light bulb is out, it could be because the light bulb, the filament broke, or because there's no power going to the socket. If I tell you that there's no power going to the socket, you have no reason to think that the filament is broken. And that's because no power going to the socket guarantees that there will be no light. And so it's perfectly deterministic, and therefore that's what you would infer. And it would be a mistake to infer the filament is broken when I tell you there's no light going to the socket. But this is the situation if in a deterministic world. We do not live in a deterministic world. Instead, we live in a world of soft constraints. Even when we try to get a situation to fully determine your behavior, we put people in prison and try to keep them in prison. We really, really, really want prisons to encourage people to stay in prison. That's about as constraining of an environment as we can think of. People still escape. So no matter how hard we try, we're really not quite capable of making a social system that's nearly as deterministic as a light as current flowing through a wire is to a light bulb. So what would happen if we were doing this kind of social inference in a soft probabilistic system? So we still have two causes, situation and disposition, for the sake of, if I'm not showing any math, because I don't know if people like seeing math, we're just going to assume that the situation and disposition both have soft constraints. We're going to say that they're technically additive and log odds for encouraging the behavior. So let's say you see a pro-Castro essay, and I tell you the situation is very, very strong, favoring Castro, favoring a pro-Castro essay. You would then expect nothing to be inferred. This is and if you instead are in a very, very anti-Castro situation and write a pro-Castro essay, you yourself must have very, very strong pro-Castro opinions. And on the other hand, if you see an anti-Castro essay in a strongly anti-Castro situation, you infer nothing about the person. And if it's a strongly pro-Castro situation, you infer a lot about the person. But these limits here, 6 and -6, are basically saying that something like 99.999% of people put in this situation would write the essay in the direction that they were instructed to. Many of us teach undergraduates who are sometimes told to write essays, and in my experience, it is nowhere near 99.99% of students who write essays as instructed. Some of them don't write essays at all. Some of them do something entirely different. So probably a more realistic scenario about how strong is the situation of being told to write an essay in one direction or another is somewhere maybe, let's say, over here, which is 90% of people would actually write an essay in support of this position. And if you're somewhere over here with a situation that somewhat favors that you would write a pro-Castro essay, you would still infer a little bit less than you would if there was no situational pressure for writing a pro-Castro essay, but you'd still infer just maybe a little bit of influence of the disposition because the situation wasn't entirely deterministic, and therefore you infer a little bit less, but still a little bit. So insofar as this is what's going on, we can see how this matches the classic experiments in the fundamental attribution error, assuming that these instructions to write essays and the various other manipulations that have existed aren't fully deterministic. What we get is essentially all the classic patterns. There's the Jones and Harris result of stronger inferences in the choice condition, weaker inferences in the no choice condition, but still inferences in the same direction. In this slightly more interesting pattern, what happens is if you see a weak anti-essay, or a weak pro-essay, that I tell you this essay isn't very, very much in support or against the position being advocated, while the person had no choice about which position to take, you actually infer the opposite direction. You see a weak anti-Castro essay when the person was told to write an anti-Castro essay, and if it's weak, that basically suggests that they themselves must be pro-Castro. And that's exactly the kind of pattern you get from this sort of probabilistic attribution. And of course, there's nothing special about situations or dispositions in this case, so we can of course invert it by conditioning on disposition and behavior, and you get the quattrone effect of basically the fundamental attribution error in which people over-attribute to situations compared to what you'd expect. So in this case, the sort of classic bias that was described was really based on a fairly naive view of the world being deterministic, and therefore we can use Boolean logic to figure out what inferences are justified. But if we assume that the world is not deterministic, we have to use not Boolean logic, but Bayesian logic, and then we see that people are doing something really quite sensible, and it makes sense of the effects without necessarily postulating two contradictory biases, one in one case, one in the other case. That make sense? All right. Next, I'll tell you a little bit about biases in memory. I'm not going to go into great detail about it. A lot of my work is on visual memory and visual perception, but I figure this isn't the crowd for that. but I'll tell you a little bit about it because it's somewhat relevant to things like the verbatim effect and stereotyping. The verbatim effect says that you tend to remember the gist of things rather than the literal description of what you saw. And stereotyping is that things tend to get biased towards their group in some capacity. So this is work done with Tim Liu, and we've done a number of experiments on it, but perhaps the most fun to tell you about is a simple iterated learning experiment with visual memory. So what we're going to do is we show a whole bunch of dots to a given person, and we take them away, we ask them to reproduce those dots. And then whatever they reproduced, we're going to show to the next person, and they're going to reproduce them, and they're going to pass it on to the next person, and they're going to reproduce it, and then again and again. So this is basically like a game of telephone, pretty much exactly like a game of telephone, except for with dots, and it's much more boring than a game of telephone. What we get out of this, though, we do this over any given chain of iterated learning is going to be 20 long. We have many chains. What we get out of this is a way of measuring what kinds of expectations people have about the structure of displays. So every time you perceive this display, you don't quite perceive it perfectly, and there's going to be a little bit of a deviation. And insofar as these deviations are systematic, over the course of this chain, you'll get some convergence towards what people expect to happen. So here's an example of 10 chains from one starting condition. So we had many chains from many different starting conditions. And you can see what people kind of converge to. There's lots of interesting structures, and this pertains a lot to things like Gestalt perception and so forth and so on. But what I want to point out to you are things like, where are we? Like that guy over here, where we converge to some groups, we converge to some lines. We can try to characterize what people converge to. What we do is we adopt essentially a clustering algorithm to infer what's going on. We also have a model of how people are doing this task by assuming that they themselves are doing some kind of visual clustering. And without diving into great detail about the actual results, the basic summary is that people converge to seeing a small number of distinct groups. They believe these groups to be self-similar, very compact. They assume them to be sort of homogeneous either by virtue of being tightly clustered or falling on a thin line. And insofar as there are multiple groups, they believe these groups to be similar, so lines tend to converge to be collinear and of equal length. So what this is getting at basically is that people aren't remembering the exact details. What they're doing is they see this display, they're inferring something about the structure of the display. What are the groups present? Any given object in the display ends up being biased towards the group, and people largely reproduce the groups more effectively than the individual objects. And so what you basically have are things like verbatim effects, things like stereotyping, the fact that I inferred that this guy was in this group, I now refer to him as being more similar to the group. So these kinds of things arise from if you see the statistical structure of the world, your individual perception of individual things is noisy. The rational Bayesian thing to do is to use the structure that you've inferred to adjust, however much needed in light of the noisiness of your perception, your estimates for any single individual. In this case, a dot. So what the most relevant thing to take away here is when people see a group, basically every individual member of a group converges towards being more like the average of the group. This yields a slightly different bias. Now, it's sort of cheating to say that we're explaining a different bias because this one is only in Wikipedia because of us, so it's our fault. I apologize. This is work done with Drew Walker. And what we're doing here is we said, well, if people tend to see a group, individual members of a group, as being more similar to the average of the group, one other fun fact is necessary, which is that if you look at the average of many different faces, the average of many different faces is attractive. More attractive than the individual faces that make this face up, that make the average up. These two faces are averages of people from Sydney's Bondi Beach, so they might have been, all the members could have been attractive to begin with, so this might not be a fair comparison. But in general, you sort of make sense why an average is going to be more attractive than any individual. Like my nose is crooked to the left, your nose is crooked to the right, we average them out and we are sort of symmetric, right? More importantly, things like various skin blemishes get averaged out because in the average, nobody has the same skin blemish in the same spot. Averages are attractive. So we wanted to know whether this kind of averages being attractive, individual members being drawn to the group average, is going to produce essentially something that on the TV show How I Met Your Mother was described as the cheerleader effect, in which the ostensible claim is that if you see people in a group, they're more attractive than if you were to consider them in isolation. So we did many experiments on it. Here's one of them. We asked people to rate different members of a group photo in either alone or in the group. And then we saw how attractive they rated the same face, the same photo, the same person, either cropped out of the group or not. Sometimes we compose the group photo by putting several different portraits together. It works however you do it. In all of these cases, there is a very small, very significant, but very small effect. That effect is enough to take you from, say, the 49th to the 51st percentile of attractiveness. It is not a very large effect, but being in a group helps you become more attractive. So this might seem like some kind of, here's another weird bias and effect, people in a group seem more attractive, but the point here is not that this is another weird effect. The point here is that this is all arising from exactly the same process that the dots being biased toward the average are, which is that any individual in a group ends up, because it's not perfectly perceived, ends up looking more like the average, and in this case, it yields a more attractive face because average faces are more attractive. So those are the cases that I told you about, the ones that are underlined. Other people have described how rich probabilistic reasoning could yield effects such as framing, which is stuff done by Craig McKenzie largely, how gambler's fallacy and the hot hand fallacy, this is work by Dick Aslan and Paul Schrader and others, and a number of other things. Any questions on this part? The basic gist of the things that I said are that if people are doing some fairly structured and probabilistic reasoning, you get various kinds of biases without having to postulate specific biases to explain the effects. Yeah?
Can you just briefly re-explain how it is that the probabilistic element makes people more attractive when they're in groups?
How the probabilistic, so if I see a face, I don't know, I'm not quite sure of all the features of this face. Just like if I see a dot somewhere, I'm not quite sure of its properties, like its location or its size. And that dot is going to look more like its group average, because a noisy persub gets biased towards sort of the hierarchical mean because I'm using the group properties as the prior for this individual, so that gets biased toward the average. For the face, I have noisy estimates of face features, and I have an average face for this group because I extract the average of this group when I see it, and I get biased towards this average in terms of the features of the face, and therefore the individual face looks more like the average face.
So would you predict then that as it becomes more uncertain, you would get a stronger effect?
You would, and the way in which we tried to measure this didn't quite work, although but that is exactly what would happen. That's exactly what I think would happen.
And you've done this not from memory, but from actual, they're looking at them right now, so you're not actually having them do it from memory?
This is from memory.
Oh, this is from memory.
It has, yeah. I think if you did it with them looking right now, then they can just move their eyes to this thing and to each individual face, and there would be no uncertainty. Yeah. Yep. Okay. The next part that I'm going to tell you about is various kinds of biases that might arise from resource-constrained inference. So the kinds of things that I told you about rely on doing some kind of probabilistic inference, whether you're inferring the structure in the display or you're inferring what is the likely situational force in light of this person's disposition and behavior. You have to represent probabilities somehow to do probabilistic reasoning of the sort I'm describing. And how on earth do you represent probabilities in your head? There's a few possibilities. One is that you can walk around with analytical expressions in your head, like probability density functions for various kinds of things, and then you combine them in various ways. That sort of seems a priori implausible. Another possibility is that you can have a tabular representation, in which basically you're going to list every possibility along with its associated probability, and thus you're going to enumerate the options, and by enumerating the options you can thus know the distribution of probability across all options because you have a table of all the options, and there's folks who suggest that the various parts of the brain are doing some version of that. What I'm going to tell you about that I think captures some of what people do is that you can also represent probabilities by having essentially a machine that generates samples. So if I have a Plinko machine like this one here, every time this ball drops down from the top, it'll bounce either left or right randomly. And if this Plinko machine is large enough, in the end what I'll get is a Gaussian distribution in the bottom by virtue of the central limit theorem. So if I have this machine and I can drop a ball through it whenever I want, I effectively have a representation of a Gaussian probability distribution. Because if I can obtain a very large number of samples from this Gaussian, I effectively have a probability distribution from the Gaussian. If I can get a histogram of samples, that's effectively the same as having a representation of the probability density. So if I have a way of generating samples, then I have a way of representing probabilities, and there are various sophisticated ways of trying to combine these sample generating mechanisms to do inference. So what I'm going to suggest is that people do this kind of probabilistic approximate inference by sampling. This is a fairly general, it's fairly scalable approach in statistics and machine learning that uses probabilities. It's much more effective than trying to analytically solve equations. It's certainly more effective than trying to enumerate all the possibilities, especially when you're dealing with infinitely large hypothesis spaces. It's psychologically plausible, and it's kind of weird. I'm going to say it's psychologically plausible and cite myself as saying it's psychologically plausible, and therefore it's true, right? It's like a Wikipedia self-referencing itself as a. But let's just say it is. Other people said it's neurally plausible, and let's just trust them. And I'm going to tell you a little bit about how this actually predicts and describes some human idiosyncrasies. So if people do this kind of inference and decision making by sampling, what do we expect? Do people actually do this kind of sampling? One way to see if decisions are coming from independent samples can go back to Francis Galton. That little Plinko machine, that also should be credited to Galton. So he invented it. So Galton's getting all the credit here. So in 1907, Francis Galton published a paper after he went to a country fair. In that country fair, there was an ox, and people guessed the weight of the ox. And the closer the person who guessed the weight closest would win the ox, and I guess get to take it home. But I guess in 1907, that was a big deal. People wanted the ox. Lots of people played. They made many guesses. What Galton found was, well, actually, Galton didn't actually look at the mean. Other people did. He looked at the median. Nonetheless, what he found was that the average of all of these guesses was really close to the correct answer, much closer than any one of the best guesses was. Now, to Galton, this made him question this notion that that the country should be led by the elite aristocrats who know what they're doing, whereas the unwashed masses who don't know what's going on shouldn't have a say because they don't know what they're talking about. Presumably at this fair, there were a bunch of experts about oxes and a whole bunch of ox idiots. But in the end, even after aggregating all the guesses from these unwashed masses of people who know nothing about oxes, you still get an answer that's closer to the correct truth than even the most expert guess in the crowd. So this made him change his views on democracy. We needn't go that far if we don't want to. What this really reflects is a basic property of independent samples. Insofar as you have independent samples from a distribution, the average will converge to the mean. If insofar as the distribution is unbiased, it'll get pretty much right on the answer. So independent samples averaged together get you close to the correct answer. So this is how we can test, at least at a superficial level, whether people make guesses by sampling. Insofar as we can get this wisdom of crowds effect from multiple guesses from multiple people, if individual people are doing something like sampling, we should be able to get a wisdom of crowds from multiple guesses from a single individual. So what we did is we asked people to answer a bunch of weird questions that we derived from the CIA World Factbook. Things that presumably they didn't know and couldn't look up easily, like what % of the world's airports are in the United States, or Saudi Arabia consumes what percentage of the oil it produces, and so forth. Normally I have the answers, and I don't know if this crowd is really interested in knowing these answers, but I don't have them in this presentation, so you're going to have to just not know for a while. I apologize. You'll get over it. So what happened? When they made their first guess, they were sort of wrong. Then, to their dismay, we asked them to make a second guess that was different. We either did this right after they made their first guess or after a 3-week delay, meaning the second guess came after a 3-week delay. In both cases, the first and the second guess got worse, presumably because they thought that they already made a good guess. Why try? And this is stupid. But if we average the first and second guess, on average, of a single person, on average, the average of the first and second guess of a single person is better than the first guess or the second guess. This is mean squared error on the y-axis. This benefit increases with a delay. So this is a slight benefit here, and this is a much larger benefit after a 3-week delay. So what you have effectively is this kind of wisdom of crowds effect from a single person, from within a single person. So it's kind of like a person has a crowd in their head, or without being too allegorical or whatever, they're sampling, or something like sampling. We can ask, are they doing something like sampling from distribution that kind of reflects the world? There's sort of a few ways in which this could have come about without them doing sampling from a distribution. So we can ask them to estimate the prices of real-world things. So we're going to present people with sort of a class of object. Here's a diamond solitaire ring. We'll have them move this slider to and fro to estimate how much it costs. And we'll make them do this for a bunch of objects. We'll make them do it a bunch of times for each object over the course of a while. There's sort of more stuff going on here, but what's more relevant for our purpose is how variable are these guesses across people and within people. The first question, of course, is, are people doing something competent? Each of these objects, here's its average price as extracted from Google products. And here's the average price that people said. That's the identity line. People sort of know how much stuff costs. That's encouraging, because otherwise what I'm going to tell you next wouldn't be particularly meaningful if they didn't at least get the average right. So we can ask, how does the dispersion of guesses vary across individuals, and how does that compare to the dispersion of prices in the real world? So on the x-axis here is the standard deviation of prices for that category. On the y-axis is the standard deviation of average guesses across people. And that scales, quite as it should, with the standard deviation in the real world. So for whatever this thing is, like some kind of necklace, necklaces are highly variable in their price. And different people, on average, have very different opinions about the price of necklaces. So that suggests that the distribution, at least, is captured in the crowd. But to what extent is any individual capturing something like this distribution or the variance? The answer is somewhat, but a whole lot less. So the standard deviation of guesses within an individual for that same object also increases with the standard deviation of the real-world prices. But it's nowhere near the identity line. So it's definitely going up for objects that are more variable. Guesses from a single individual are more variable. But it's nowhere near the variability across people. So this tells us that, well, in some sense, this does reflect a distribution because it scales with the real-world distribution, but it does not reflect a very well-calibrated distribution. And there's any number of reasons why this could be the case. One of these is different people see different products. I shop at Walmart, let's say, and you shop at Neiman Marcus, and you're going to be exposed to a very different distribution of prices in the real world, which will then produce variance across people, but not within. Another reason why this could happen is that people might be reusing their samples. And one evidence for people reusing their samples is this fact that I told you earlier, which is that if I wait 3 weeks before asking you to make a second guess, the benefit of averaging your two guesses will be greater than if I do so immediately. This suggests that if you forget your first guess, your second guess is more independent. So we can sort of quantify how much more independent by asking how many different people is a second guess from you worth. That's just basically putting a number on that difference, and if I ask you for a second guess immediately, it's worth about 10% of a second person's guess. If I ask you after 3 weeks, it's 35-ish% of a second person's guess. Still not great. But if people are reusing these samples, and that's why they're not quite independent, what you might expect is that people who can't remember what they first guess would do worse, but would get a greater benefit of averaging their guesses. And that's exactly what happens from Kathleen Hurahan and Aaron Benjamin. They asked whether people who have a low working memory span, generally people who have a low working memory span do worse on most everything. Just most things end up being correlated in terms of cognitive performance, and having a low working memory span correlates with doing worse on most things. However, in this case, having a low working memory span means that this crowd within benefit, the benefit of averaging multiple guesses from the same person, is greater for them because they can't remember their first guess as well. So their second guess is more independent. So I think at least some of the reason why variability within people is smaller than variability across people, is that people are reusing their samples. But in the end, people are doing something like sampling. But if they're doing something like sampling, it seems like they're using a very small number of samples and they're reusing them a lot. And this notion of having a Plinko machine in your head to represent a distribution only actually represents a distribution at all faithfully if you generate a whole bunch of samples and get a histogram. If you just generate one or a few samples, that's not going to represent a distribution at all. So why are people just using a few samples? Is this a bias or not? To tackle this kind of question, we adopt a rational agent framework, which is basically an expansion of the classic sort of perception action loop that's often used for motor control and other such things, which is that people have some model of the world, they have some expected reward. Based on their model of the world and how they expect the world to reward them if something comes about, they form a policy about how they're going to interact with the world. They'll take some action that influences the world. They can measure the world with their senses, and then they update their world model, and this continues. So they plan as well as they could and make actions to maximize utility. But we can supplement this by saying, well, perhaps people also are doing this kind of process in their heads. Perhaps they're choosing how much to sample or what to remember and things of that sort in exactly the same way. Perhaps they're trying to optimize the usefulness of their thinking. Perhaps thinking isn't free, and you can figure out how much you should think. The intuition for what I'm going to tell you can probably be best described by throwing pieces of paper in a trash can. If I tell you that you should need to throw this piece of paper into that trash can at that distance, and I asked you just how hard are you going to aim, in that case, you're not going to aim at all, right? It's like trivial. There's no, even if you get nothing from trying to aim carefully. You'll just toss it in and it'll go in because there's zero uncertainty compared to how rewarded you're going to be. If you get it into the trash can, it'll go in. You don't need to aim carefully. If you're throwing that piece of paper into that same trash can from very far away, let's say the Leaning Tower of Pisa, there's really no amount of aiming that's going to get you anywhere near it, right? I mean, you can aim really, really carefully, but the gusts of wind are too unpredictable. No matter how carefully you aim at that trash can, it's still going to be a crapshoot whether it goes in. Your best bet is just to throw it off the right side of the Tower of Pisa, but that's about as careful as you should be. But at this interim distance, perhaps this is exactly where you should be aiming carefully. So how hard you choose to think, how carefully you choose to aim, really the conditions need to be just right for it to be actually worth it for you to think carefully and plan. We can ask just what kind of conditions are necessary for you to take many different samples rather than just take a few samples. We can do this for a scenario of two alternative force choices where you're choosing between two options. So the reason that we're going to talk about two alternative force choices is that there's a bias that people describe, which is the probability matching. If I tell you that option A gets rewarded 70% of the time, option B gets rewarded 30% of the time, the thing that you should do is choose option A all the time and maximize your rewards. Instead, what people do is they choose option A 70% of the time and option B 30% of the time, modulo some exponent. So that's why we're dealing with two alternative force choices. So what we're going to do is we're going to say, well, how good is your decision going to be on average if you're making these two alternative force choices? If you take 0, 1 to 1,000 samples. If you take 0 samples, you're at 50-50 on average. If you take a whole bunch of samples, on average, you're at 75% accuracy because sometimes the two options are 50-50 and sometimes they're 100-0, and on average, if you marginalize over the full set of possible probabilities that it could be, you get 75% on average. And now we can say, how many decisions do you get to make per unit time as a function of the number of samples and how hard it is for you to generate a sample? And here, generating a sample, the only cost of generating a sample is the cost of thinking. It takes you a little bit of time to generate a sample. And as you generate more samples, you get to make fewer decisions per unit time, right? Because you have to take longer to think about each one of them. And then we can multiply these two functions together to figure out what is the expected utility per unit time. What is your rate of return for making decisions with this amount of thoughtfulness? And for each one of these curves, which corresponds to essentially the time cost of a sample, we can find the maximum and decide, and that will tell us what is the optimal number of samples for you to take to maximize your rate of return. And across a very, very wide range of basically the cost of a sample in terms of time, the optimal number to take is 1, or 0, 2, 3. It really needs to be the samples need to be really, really dirt cheap compared to how long it takes you to execute the action for it to be worth taking even 30 samples, let alone sampling until you get a perfect fidelity representation of the probability distribution. So what you see is that making many decisions sort of badly is the best thing you can do insofar as you have a time constraint and are trying to maximize your rate of return. So people are using a small number of samples because it's sort of the best thing they can do. And if people are using a small number of samples, there's a few weird things that happen. One of them is black swans. So let's say what I'm going to do is I'm going to imagine scenarios by sampling them based on their frequency proportional to probability, and then based on the scenarios that I sample, I'm going to figure out what is the best thing to do. And now let's say I'm playing Russian roulette. And let's say that I'm playing Russian roulette with a much larger revolver. Let's say it has 30 chambers. One of them has a bullet. So 29 out of 30 chambers don't have a bullet in them. And if I were to just sample a single scenario from this, I would probably sample a scenario that there is no bullet. Therefore, my reward is going to be very high because, it's a small reward, but with 0 risk. Of all the scenarios I've sampled, I've never beshot myself in me imagining the future. And of all the scenarios I've sampled, I've gained a little bit of bravado from sort of shooting, from like pulling the trigger. But because I never sampled the rare, but really, really, really important scenario in which the bullet is actually in the chamber, I don't realize that there is a very low probability and high stakes scenario. So this kind of black swan, low probability, high stakes scenario would be grossly underweighted by using a small number of samples, and that would mean that you would effectively end up shooting yourself unnecessarily, more or less. We can sort of draw a picture of you shooting yourself. Here's the probability of the extreme value of the state. Here's the stakes of that state. And if the probability is small and the stakes are high, the probability of you shooting yourself, or basically the loss compared to doing the loss of making a decision based on a small number of samples compared to making the decision based on the full probability distribution is very, very high. We can get rid of this. We can do away with this problem of using a small number of samples if we were to do a version of sampling called importance sampling, in which we weight the samples that we draw based on their stakes. So we can correct for this after the fact to some extent if we have enough samples. We can sort of sample not just proportional to frequency, but proportional to frequency multiplied by the stakes, roughly speaking. And then correct for it after the fact. And then we get rid of this you shooting yourself inadvertently lump in this loss function. But what we get instead is if you were to try to make a guess as to how frequently the bullet is in the chamber, how often this high stakes, low probability scenario actually comes about based on your small number of samples, what you get is an inflation of low probability scenarios. The probability that you would estimate for the occurrence probability you estimate for low probability scenarios that are high stakes is grossly inflated, which is effectively a version of what's known as an availability heuristic or an availability bias, or one version of it, in which very extreme and salient events end up being overweighted in their probabilities. And one potential explanation is that you're making decisions based on a small number of samples and trying not to shoot yourself with a black swan. I'll tell you about some other stuff that we've sort of worked on, and then we'll wrap up. If anybody has done this kind of approximate inference by sampling in their own statistical endeavors, for instance, you might know that it is not actually trivial to get a sample of the thing that you want. In fact, we have to come up with clever algorithms to do it. One of these, and so the question is, do people adopt such clever algorithms? And does this give us any sort of purchase on biases in human behavior? So the kind of algorithm that I'm going to tell you about is known as Markov chain Monte Carlo, which basically says that I'm going to generate samples not by running this little chain that evolves according to some rules in which I start somewhere and I'm going to choose to go one way or another way based roughly on a coin flip weighted by how effectively it's matching the thing that I want to match. And this is efficient. You don't have to evaluate the whole probability distribution. You don't have to be able to sample from the whole probability distribution. You just get to adopt a fairly simple rule for meandering around in this chain, and that will eventually get you the probability distribution you want. If you adopt such an MCMC rule for generating samples, and what you get is a few interesting patterns of behavior that match the dynamics of some aspects of human cognition. So one aspect of the dynamics of human cognition that we've described that might arise from this kind of MCMC sampling is inference in binocular rivalry. In binocular rivalry, the scenario in which you see one picture in one eye, another picture in another eye, and what happens is you see the thing on one eye, and then it switches to the other eye, and then it switches to the other eye, and there's a few other things that happen. And with a fairly simple model for how you do this kind of inference with seeing two pictures in two different eyes and doing MCMC effectively on this model, we get many of the characteristic dynamics of the switching behavior. A similar thing happens for word problems. If I give you 3 words and ask you to come up with a single word that goes with them, this is known as a remote associate test. But what I'm going to do is not just ask you to provide one guess. I'm going to ask you to just keep guessing until you figured it out. Just keep producing guesses. What you get is essentially a string of words. And those words tend to meander around what folks call semantic space. And the dynamics of how your guesses meander around the semantic space are pretty well described by essentially MCMC over this semantic space, this chain wandering through semantic space in search of a word. So I'm not telling you nearly enough details for you to evaluate it. You can either trust me or not trust me. But the claims that we've made, which I think you should take with a very big grain of salt, is that some dynamics of human cognition seem to be consistent with this kind of Markov chain Monte Carlo. And others have argued that the kind of argument I made about using a small number of samples if you're generating correct samples also applies if you're running these kinds of MCMC chains. Like even if the chains that you're starting with start over in weird locations that are biased, it's still better to just take a small number of steps and just call it quits than to run your chain for a long time to come up with a good guess. And insofar as that happens, your initial bias from where you start decays slowly, and you get something that people have called the anchoring effect. So using a small number of samples generated from an MCMC chain might yield anchoring to some extent. So altogether, what I've at least waved in the direction of is that people tend to reason via structured probabilistic models. It gives them various kinds of characteristic memory biases and a few other kinds of errors. They seem to do so via sampling, and they seem to do so via sampling in a resource rational way, which together gives you a pretty good account that can capture many, certainly not all, human successes and failures, namely these blue and red ones. Okay, thank you. Yes.
So I have a question about the cheerleader effect, and this is just, maybe I'm revealing my ignorance of cognitive science, but if I understood your explanation correctly, then it should be the case that we see averaging in memories across sets for lots of things. So if I show you 10 color chips and I point out the third one and I say I want you to remember that, and then I take them away, and then you have a choice as to which color that chip actually was, it should be the case that the others present in the display will affect your memory.
It does. That does happen, yeah.
All right, so.
Yeah. I mean, that definitely happens. It happens for things like size and color. Color is a little weird because it's normally when people manipulate color in these kinds of memory experiments, they do so on a circle. They just use hue angle. And if you don't put any structure in the group, your average is basically neutral gray, so there's no bias. But if you impose some structure such that the average of the hue isn't at neutral gray, then you get exactly the kind of bias that you're describing.
Okay.
Yeah.
Kind of a slightly open-ended question. I more want to hear your feedback on the general thing. So, first of all, that was really compelling, and I'm glad that you came and shared.
It shouldn't have been that compelling.
No.
You should be a bit more skeptical.
Right. Hold on to the second part. So the second part is, it's really bold to present it to a bunch of evolutionists as well, because our kind of bread and butter is looking at domain-specific computational, adaptations and other kind of things that are doing specific kind of work. But I really take your point, and I think a lot of people would maybe have a crude sketch in their head that the brain and the mind is starting with a template of a lot of these kinds of probabilistic statistical approaches and so on, and then for various reasons, maybe reasons that are selected over phylogeny, you get a refinement, and now you have a widget that, while in most respects is sort of drawing on these general purpose procedures, it's specialized. And I think this kind of model could be really good as a strong control condition in work trying to demonstrate the psychological reality of those things. So as a case in point, the cheerleader effect. You could spin all kinds of stories about, it's adaptive to infer greater attractiveness because
people in groups are better and they're more desirable.
They know
Yes.
things about the person,
Yes.
that they like them, they're sociable, and that's yada, yada, yada. Okay, so now say I'm taking your point very seriously and I want to conduct an experiment to rule out, or to show that above and beyond this, there's selection particular to that problem. I'm not sure how I do it, because as you were giving the talk, I stopped and thought, okay, well, I know
we actually thought about doing this because I'm pretty sure that in the real world, something like a cheerleader effect is much larger than what we saw. We saw something that is good enough for 1/20th of a standard deviation of attractiveness. That's a very small amount of improvement. I bet in the real world it's much larger, in the sense if you were to go into a bar and look at people in groups versus people in isolation, the people in groups are going to be more attractive. They're going to be more attractive because more attractive people are probably in groups and less attractive people are probably alone. That's probably there. More attractive people in groups are probably happier, and they're going to, so there's going to be, so you can measure the size of the discrepancy and compare it, right?
If I'm a Boolean skeptic, I just say, people they're paying more attention in that heightened social setting with, greater, it's more stimulating, there's more relevance. So I get a bigger signal and you get a bigger effect of the group for some reason like that. But it's still, there's nothing domain specific about it. It's just this averaging effect playing out in that heightened setting.
Well, paying more attention should reduce it, as Danny pointed out. If you, the sort of being drawn toward the average relies on this uncertainty, and this kind of paying more attention thing should reduce it.
Right. Well, I guess I had in mind not so much focusing in on the specific.
On that,
person,
I see. Yeah.
being like that.
Yeah. I mean, okay. So I'll give you an example.
How do you prove yourself wrong, or to show something above and beyond?
Well, I'll tell you one example which you might like as an evolutionist. One of the domains that I study is also intuitive physics, which is how people reason about the dynamics of objects in the real world. And this is another case in which people have long talked about people having weird biases and not knowing how to do intuitive physics. One classic example of this is sort of extrapolating the trajectory of a pendulum after you cut the rope. And if you sort of show people a pendulum at a certain point and say the rope is cut here, now draw the trajectory of the bob as it falls after the rope is cut, they do something totally chaotic and wrong and nothing like physics. They don't draw sort of a parabolic trajectory. And so what we did is we asked people, we sort of wanted to know just how bad is it, because we think that people do know physics to some extent. And we asked people to do a few things. We asked people to interact with this kind of system where it's swinging back and forth, and then at some point it gets cut, and what you have to do is move a bucket to catch it after it gets cut. Or you have to, there's a bucket that's fixed, and you have to click to indicate when to cut it to get it in the bucket. Or you have to draw it in a few different varieties. And so the sort of interactive tasks, ones where you basically are engaged with your sensory motor system to catch and manipulate the physical system to get it to do what you want, show very good calibration with sort of doing the correct physical thing in light of uncertainty, the kind of story that I'm telling you here. The drawing task, people are a disaster at it. So doing this kind of explicit thing just doesn't look like they're not doing physics, they're not doing anything really consistent. So I think there are cases in which you can show that like the drawing tasks that we saw and various manipulations of them, they just never produce anything that looks like people are doing something physical. People are doing something physical in these sort of more sensory motor tasks, and it suggests that these sort of evolutionary systems, that at least things like physics are somewhat encapsulated in your sensory motor system rather than you being able to cognitively access them and draw a trajectory or answer arbitrary physics questions, even though you know what to do within the physical world to interact with it. I think the same thing is going to be true in your visual system. Like you have to invert complicated optics to figure out the 3D shape of things. And if I asked you to do that explicitly, you would have no idea how to do it, but your visual system does it just fine. So I think in some cases, it's very easy to show that people aren't doing anything that they should be doing, at least explicitly. Yeah. Yes?
I was just wondering whether, just following up on Colin's point, do you see this same kind of act versus reason on effect across a number of these biases, or are there some biases that may be evolutionarily older or more recent? I ask because I was really struck with the dot experiment with the iterated learning. And there's a recent study that shows the same patterns in baboons.
Mm-hmm. Yeah.
Simon Kirby did, looking, you get the same kinds of, you start with a random pattern and then you iterate it, and baboons get the same outputs, or get the output from the last individual, et cetera, and then you start getting lines and clusters, and you see, I think you see very, very similar patterns, and so I was just wondering, across all of these effects, do you have that same act versus reason, or is it maybe that some of the kinds of
Well, for some of them, they're pretty much you can sort of wire them up to become sort of more perceptual or sensory motor in some sense, but things like the fundamental attribution error, where you describe a scenario that somebody's in and ask to infer their disposition or the situation that they were in, you can sort of try to generate games in which it's more interactive rather than an explicit reasoning task, but for the most part people haven't done that, and I don't know if you'd get a lot of differences.
It's hard to think of like a non-verbal version, but
I presume you can probably generate something in which you see like a little agent bouncing around doing stuff, and you have to do something else to interact with it based on how you predict it'll behave in the future, which will require inferring its motives in some sense. And there are versions of this that people have done with infants, which show that you do something like that, but it's hard to get a lot of resolution on the behavior of infants, and so it's not clear just how much they infer. But I don't know if I've seen good evidence that there's a distinction between doing that kind of social reasoning explicitly versus implicitly. You can perhaps look for it, but I don't know if it exists. It could. Yeah.
So just to try and clarify the discussion a little bit, because I think this is an interesting set of points. As I understood Colin's question, it is not how, from your perspective, can we address that evolution seems to produce accurate systems. So your folk physics reply is, well, people may have a difficult time, sort of articulating their knowledge in some ways, but when they actually have to act in the world, they do the right thing. The literature that, at least as I understood it, that Colin is referring to is instead one that claims that there are biases produced by natural selection, okay? And there's debate in that literature as to whether where the biases are, whether they're biases in perception, whether they're biases in behavior, whether they're in the decision-making process. But let me give you one, and this is not, I would say, among the best supported, but it's one that lends itself perhaps most easily to the context of discussion. So two different research groups have claimed that, that people, when, for example, standing at the bottom of a building and asked to estimate its height, come up with a different estimate than when they're standing at the top of the building and they're asked to estimate its height. And in particular, the claim is always that from above, it looks like you're higher up than it does from below. And the argument here is, in the world of our ancestors, falling from heights was a significant source of injury and death. And so as a consequence, we're conservative in the sense that we tend to overestimate the risk that a structure that you might ascend poses to you. The claim is that there is an adaptive bias in there. And this literature here, to the extent that there are explanations, they're entirely proximate level, right? So anchoring works because people are doing some comparison between this. And there's no explanation about a design being in there. It's a flaw, if anything. In contrast, the literature that Colin was referencing, the claim is that there is a design. It's not a flaw. It seems to produce a mistaken output, but that's because in the long run, that's the right answer. Not in the sense of accuracy, but in the sense of enhancing fitness. That's a different question that he's asking you than the one that you were answering.
So I guess I would, this is probably the wrong crowd to say it, but I think you can tell a story about the evolutionary benefits of having an accurate estimate of height both ways, and you can bias your behavior in an adaptive way without having a misestimate of the height. That you just sort of say, I'm going to stay away from tall ledges, and I'm going to estimate the height of every ledge accurately. And so you could easily tell an evolutionary story about why it should be perfectly calibrated. So I'm not sure that the proximity versus non-proximity of the evolutionary account here is that different from the proximity and non-proximity here, because I don't know why you would favor one way for the bias to go versus another under sort of an evolutionary story.
I should say, by the way, that within the evolutionary literature, that argument has been made, exactly your expectation just now, about some of the, perhaps the prototypically claimed biases, like men's over-inference of women's sexual intent and interactions, right? And that the counter-argument has been, no, actually men are quite accurate in guessing women's sexual intent. They're just calculating expected value, and they're acting according to that.
Right.
So that is, it costs them little, and there's a large potential benefit, and so they act as if they over-inferred when they don't, right? But there's some cases that don't seem to be susceptible to that explanation.
And so the question is, do I think those situations exist, or?
No, so Colin's question was, if your probabilistic reasoning account is can explain many of the kinds of things that are typically described as biases, and the evolutionist wants to claim there is an adaptive bias that is the product of discrete natural selection in a particular domain, then yours is a strong competing hypothesis, and his question is, how do we compare them? That is, what is the protocol? Am I
Yeah.
channeling you correctly?
Well, I think the answer is that the probabilistic account predicts that various kinds of modulations as a function of uncertainty, effectively, because it's all based on uncertainty. And if you make the percept more precise or less precise, you get more or less of this bias. And insofar as you believe that there's essentially just like some kind of additive offset from the bias on the evolutionary account, that would yield a slightly different parametric curve as a function of varying stuff that should matter. I don't know if the evolutionary account predicts that other parameters should matter that perhaps don't matter under the probabilistic account, but hopefully they make more predictions than just the point estimate that there is a bias, but also show how it varies as a function of something else, and then you can see if they vary that way. But I think just from the point estimate, if you have two things that predict the same point estimate, you can't tease them apart. You have to see what else they predict.
In terms of maximizing expected values, doesn't it depend on the context as well? So, I guess it would be equally as important to understand the context under which people are making these decisions as it would to just have a baseline bias.
Yes.
So whether or not it's someone's maximizing their expected value, like this encouragement literature stuff, would also depend on the context who's making the decision.
Yeah.
So give an example about a guy approaching a person in a bar, right?
Yeah.
Well, it depends on if they're in a group or if it's an individual. Well, they may be more likely to actually approach the individual female because they're more likely to get the result that they want.
Right. Yeah. There's a I don't know if I absolutely agree with you that a sort of a more complete account should also tell you how this effect will vary as a function of context and available information. I think you can make a probabilistic account do that, but by default, like the more context you have to build in, you get to the point of having a complete world knowledge kind of model. So it's actually it's often easier to manipulate uncertainty as a prediction because you don't have to add more knowledge to the model to get predictions out of manipulating uncertainty. Whereas context, I think, is a powerful manipulation, but to get a quantitative prediction about what will happen as you manipulate context, you kind of have to know how the context influences the mechanics of the model, and that you can sort of fit it post hoc, but that doesn't really test anything. You need to measure it ahead of time somehow, and I'm not sure how.
Or come up with evolutionary.
Or come up with yes, yes,
Meaningful predictions.
yeah.
For the cheerleader effect, one thing I wasn't clear, if they were an unattractive group, would the person be perceived as more unattractive?
This is kind of like every happy family is the same, every unhappy family is unhappy in its own way. Similarly, every attractive face is sort of the same, but ugly faces are all uniquely ugly. And so you actually get a much larger benefit of averaging among a group of ugly people because their ugliness is all in different directions, so the average is more, you're averaging out more weird asymmetries.
But I could see the prediction actually being that because you're sort of like averaging the average ugliness or unattractiveness.
Well, if you think of ugliness as a feature, then the average ugliness of this group of things is high. But if ugliness is essentially a consequence of the other features being sort of aberrant, then averaging all the other features will make you become less aberrant and therefore less ugly. A post hoc explanation for.
Well, like with color, you would think that you just if they have red, pink, then you just take each individual item, get a value out of that, and then average those together versus taking the individual features. Which people, when they look at faces, they tend to take the average of the face rather than the individual features.
Okay, well, what I can tell you is that the benefit is higher for people who are less attractive. We never manipulated the group, so I don't know exactly what happens if you manipulate the group to be all ugly versus all attractive. More attractive people tend to get less of a benefit. It's not a detriment, but it's less of a benefit. And you were making a prediction, and I was saying that I think I would make a different prediction, which is that I don't think ugliness is a feature, therefore you wouldn't average ugliness itself. I think ugliness is a property that emerges as a judgment of a bunch of other features. So those other features are what makes things ugly is asymmetries and deviations from the average. Therefore, when you average those other features, you become closer to the average, and so you become more attractive. So my prediction is you get a stronger effect in a sort of a group made up of very ugly people that are ugly in their own special way. You get a very weak effect if you get a group of ugly people who are all ugly in the same way. Like, let's say everybody has like a jaw broken in this direction. The average is still a jaw broken in this direction, and it's not very compelling. It's not very attractive. So I think it will be what's going to really determine how how much of a benefit you get is how different are the deviations from the average. Yeah.
Yeah, so when you were describing the transmission chain models, you said that the updating policy that you were observing was essentially an optimal Bayesian updating policy.
Under
Rational Bayesian.
this is the iterated learning or the MC?
Yeah, the dots.
The dots. Yeah. Uh-huh.
So, I mean, given that they converge on, so I have sort of two more questions. So,
Uh-huh.
given that they converge on patterns that aren't really there.
Sure, but I mean,
and
it starts
you're
off
finding
random,
out
so
more
there's
about
nothing there.
priors, right? I mean, essentially
Yes.
what you're doing is
Yes.
modeling is prior.
That's exactly what we're after.
So, and you have to then would ultimately have to explain where the priors come from if you're not data.
Yeah, it's true.
I mean, because an optimal Bayesian agent with a flat prior looking at those data would not converge.
Yes.
Right?
Yes.
So then my second question is, given that it's a transmission chain, you can imagine sort of theoretically an agent looking at the world and trying to say, what's the real pattern that's in the world? So it's a game against nature. Versus someone who knows that they're in a transmission chain, where the prior is about the person who came before them. Maybe mixed with something about the world, right? But there's an interesting question about transmission chains. To what degree do people who are in the transmission chains, if they know that the data that they're seeing are generated by another person before them? And I don't know to the extent to which they know that in your game.
They don't.
Is there something? I mean.
I'm sure people have. I'm sure people are going to have very different priors based on the generative model they assume for the thing that they're looking at. If they think this is a drawing that somebody else produced for them, it's very different than if they think this is like a random scattering of lines.
So that's interesting in this case because the patterns that you end up seeing are way more idealized than what would normally occur in nature. I mean, I guess we could debate.
Well, in this case, they don't know that it's part of a chain.
Yeah, that's interesting. I mean, I wonder.
But I bet you would get more. So we get a few examples of like fairly high-level structures emerging, like letters. For like the most dominant things that we can measure, but that's sort of limited by our ability to model these things ourselves, are like lines and collinearities and this kind of hierarchical structure. But if you sort of inspect the things that people converge to in the end, you get things like letters and a few other kinds of figures. That's sort of a minority of the displays, but I bet the frequency of those things would increase dramatically if people know that this is an iterated transmission and what they're looking at was produced by somebody else, then they would look for a much higher level meaning than just local scene organization.
Interesting. Yeah. So it seems like it would be an interesting thing to maybe try to experimentally manipulate.
Yeah, that's a great idea.
What the generative process people think they're looking
Yeah.
at is, right? 'Cause
Yeah.
I mean, if you say these are earthquakes of a magnitude of a certain, produced on a foreign planet or something like that, are they going to converge on the letter A after?
Right.
So, I mean,
Yeah.
it's interesting that you're they seem to have these strong priors about patterning that are more consistent, it seems to me, with a agentic generation process rather than a natural generation process.
Maybe they think the researchers,
Well, they are seeing a set of dots on a computer, so it would be quite wrong of them to assume that it's a natural generative process.
Right.
I mean, it's at the very least a computer-generated process, and presumably some experimenter programmed it. So I think they probably infer something like that, but not nearly as much as they would if we tell them explicitly that somebody else produced it, or tell them explicitly that this is data from something, from some natural process. Yeah, that's a great idea.
There's another explanation, which is that they're priors, but they're a different kind of prior in the sense that they're priors in structures of visual perception rather than priors of belief about the world or about other agents, right? So if you have line detectors at set angles, right, then to the extent that that influences your memory of what you have seen, right, because you tend to parse the world in ways. I mean, those line detectors exist because they are, natural selection has produced them as a
Mhm.
parsimonious way of chunking the world, right? So the world has some
Absolutely.
structure to it. And those are in your head, then you will tend to remember
Yeah.
and accord with those. And you'll get letters, for example, because letters are the product of cultural evolution that has addressed the affordances of the human visual system, right? So they're maximally
Yeah.
distinct characters based on line detectors.
Yeah, no, I think I think the most people in vision would assume that sort of high-level knowledge is not going to penetrate to your visual system and influence your priors about the structure of a scene to that or these random dots. I sort of root for penetrability from high-level knowledge, and so I would hope that that happens, but it could very well turn out the way that you're describing, where no matter what story we tell them, we get the same stuff out. So that's it'd be fun to do, yeah. Thank you, guys.
Great.